Physically based shading. Physical based shading is a complex topic, first of all, but I will try to make it as simple as possible so you guys can understand it. And before doing any isotropic or anisotropic material, you will have an idea what to achieve for. This is a must known fact for a shader artist as well as for a technical architecture for shading the scene. It's a combination of physics and maths. So, first of all, what is light from a physics standpoint? It is a technically an electromagnetic transverse wave that sounds very advanced, but it actually means that the electromagnetic wave wiggles sideways as the energy propagates forward. And this wiggling is due to the electric and magnetic fields. They wiggle at 90 degrees to each other. Two common terms used for electromagnetic waves. One is the frequency and other one is the wavelength. So what is frequency? The number of wiggles they do in a second, and the wavelength, the distance between two wave peaks. The engineers have to deal with electromagnetic wavelengths ranging from gamma waves that have wavelengths of less than 1/100th of a nanometer to extremely low frequency radio waves. Those waves are tens of thousands of kilometers long. But the question is, what we can see is mostly matters to us. For your information, the range that we can see with our eyes is from 400 nanometers for violet light to 700 nanometers for the red light. Now, to give you an idea what 400 to 700 nanometers actually is, because the physical size of this will become relevant later in the video. As you can see, the hair strand and the silk of the spider. The silk of the spider is 1 micron in width, which we can see with our naked eyes. And the thin line in the strand is a spider silk. What I mean, you can see a strand of spider silk with your naked eyes, and that is roughly 10 times smaller than a human hair. So till now, what I'm trying to explain you is that the fairly simple sine waves, like just a single sine wave is propagating into a medium. But this is not a common type of light wave because most light waves contain many different wavelengths with a different amount of energy in each. And here a new term arises, SPD, which means spectral power distribution. You can see the SPD for different light waves. For lasers, the Dirac delta function prominently in the SPD graph. A quick introduction to Dirac delta function. It is used to model the density of an idealized point mass or point charge as a function which is equal to 0 everywhere except for 0 and whose integral over the entire real line is equal to 1. Yeah, I know it's hard to understand, but let me make it simple. In optics, the Dirac delta is regarded as a kind of limit, a weak limit, a sequence of functions having a tall spike at the origin. Lasers, let's move forward. Lasers actually have a little bit of bandwidth, but they are extremely narrow. Notice the SPDs for red, green and blue laser that is multiplied by a factor and added together to produce SPD. This kind of SPD is similar to what you see in laser projectors, and they mostly show up in higher end theaters. What is so special about it? They offer wide contrast, wide gamma, and if we look at the actual waveform, we can see that after adding up these three simple sine waves, we get a little complicated than a single sine wave. Some underlying frequencies and some larger peaks. This is the kind of thing you see in natural light or D65. D65 is a standard spectrum for white light, outdoors light, and the waveform that it will create is of course very complex. Now an interesting thing is that although these two SPGs could not be more different, one is extremely smooth and broad and the other one is Dirac delta function, that they have the exact same color appearance to humans. And the y-axis is the same scales. Spikes are higher to compensate for the lack of width, but what is the fact here? That the human color vision cannot distinguish between these two signals. Let's try to put the infinite dimensional SPD down to a three-dimensional perceptual space. A waveform inside a vacuum will propagate forever, the electric and magnetic waves with reinforcing each other and just keep on going and going. But for rendering in computer graphics, when this light wave interacts with the matter, what happens? This is what we care about. In reality, an electromagnetic wave hits a bunch of atoms or molecules, it polarizes them. That means it stretches this end and separates the positive and negative charges and form dipoles. and this absorbs energy for the incoming wave, and this energy is radiated back out. You can imagine this work like a spring. Then the dipole sort of snap back, and this energy is rear outwards, and sometimes some of it is lost in terms of heat, or other times all of it is preserved and radiate outwards in new waves going in all kinds of directions. In most of the gases, if we talk about gases, the molecules are far enough apart that you can treat them individually, and the mathematical and physical formulation are quite simple to understand. But in other cases, it bends. And the homogeneous medium through which light travels in a straight line, the homogeneous medium is an abstraction because matter composed of atoms can never be truly homogeneous at all scales. The optical properties of this homogeneous medium are described by its index of refraction, or IOR. And this is a two-part number. One part of the IOR that describes the speed of light through the medium, and the other one describes how much light is absorbed by the medium. And there are many medium that is completely non-absorbent, and for them that number will be 0. And we have these abrupt IOR discontinuities, and they scatter the incoming light over various directions. The conclusion is that the overall appearance of a medium is determined by the absorption and scattering properties. Let me give an example for this. The milk is caused by high scattering, low absorption. It helps to understand that absorption and scattering are two independent axes. If a liquid is colored, that means it absorbs light more readily in some wavelengths than others. After this long overview, let's jump to the physical base shading and the theory in games and movies, because that was the base part to understand something which is reliable related to the games sector or production sector. The most important factor about the surface is its roughness, and this plays a really very important role in defining a map and defining the behavior of light while rendering a scene or in a real-time render. As we know, no surface can be perfectly flat. It always has irregularities at the atomic level. Irregularities that are of similar size or smaller than the light wavelength, known as the nanogeometry in CG, and these caused a phenomenon called diffraction. After this sort of talk, you will definitely be familiar with the diffusion of light, which helps to understand all the maps in your workflow. But there is something called the Hahn-Fresnel principle that can help you understand the diffraction. Let me give you just a little example. Each point on a planar light wave, because the light wave travels in a planar direction, just imagine, try to imagine all these things, that each point on a planar light wave is the center of a new spherical wave that's being emitted, and then these spherical waves will interfere with each other in order to create a new plane wave. Hard to understand, I know that. But think about the ripples in water. Try to Google it to understand, or do let me know. I will make a video on that with full description. But for a basic overview, which helps you to understand this topic, when the point on the planar light wave makes spherical waves, the end side of the wave is not getting cancelled by any other wavefront. So the light is kind of bending around the corner, and it's not actually traveling a straight line. That's why your shadows will be very slightly soft due to this effect.